Okay, let's just get started with the material. Oh, by the way, I looked through the grades from midterm. You guys did great. Well, even though I'm not sure how many attempts exactly I gave you, but
Oh, it was multiple for the exam?
yeah, I thought it's multiple.
For each question?
Yeah, I think
Yeah, for each
they
question.
were, but the ones for where you had to choose like the multiple choice part.
Yeah,
If
multiple
you do
choice.
the first time, then that's the next. So I actually
Yeah.
got the right one, but it wasn't really recording. I was because all of them had a check, and then except for this one, I think it was like the second or third one.
Okay.
I just could like it wasn't like marketed, so I was just like I can't even like submit the test because I got it on the second attempt. Like, I guessed one and put in the second one. It says correct on the bottom, but it doesn't say check. Like if you look at the number of questions.
Okay.
So I kinda
Yeah,
like-
just do not forget to put something in. Just
Yeah.
make your choice for those multiple choice questions. Yeah, I think that makes sense, right? It would not allow you to try everyone,
Yeah.
every option. Okay. Well, that's for the midterm. I think for final would be I'm trying to keep it like the same level of difficulty, and yeah, would be similar. So let's just get to our new material, chapter 8. So our chapter 7 was not included in the midterm, so it will definitely be included for the final. And it is one of the most important chapters. Confidence interval is important. Hypothesis testing for this week is also important. Okay. I like to show everything here. So far, we talked about point estimates for the mean. And also we talked about doing a confidence interval instead of just being a point estimate. We want to get an interval around the estimate, so we are relatively sure that the real value will be in that, following that interval. So what if we have an idea of what the mean should be, and we want to use the data to test our belief, to test that theory. So for example, I think the average height of the UHD student is 5 feet 7 inches. And then I collect data. So this is my idea, like my theory, and I want to test the odds if this is true or not. So this is about the whole population, like all the UHD students. So I collect a sample of data. I have like a sample of size 10 students and got the sample mean being 5'8". So we're asking the question, could a 5'7" be the true population mean? So we would say probably it is, but because we know there is randomness when we collect the data, like measuring the height. But what if we have like 10,000 students collected and got the sample mean being 5'8"? Now, what is the chance of 5'7" being the true value of mu? So in this case, we got such a large sample, and we find a slightly higher sample mean. And in this case, we probably cannot see this 5'7" is true value of mu, of the population mean, because this is quite a large sample, is very representative already. But for this case, it's hard to see. We cannot see it's probably okay, probably not okay. So we're going to do a statistical testing to draw a conclusion from that. So for the hypothesis testing, we have two things: our hypothesis, and we will also collect some data. We got a sample from the population. So the hypothesis testing is that we can use some statistical knowledge and the data to draw a conclusion about our hypothesis. So the belief that we have about the population. And there are different types of hypotheses, but for now, we're going to work with this one sample hypothesis testing. There will be two sample hypothesis testing as well. And we'll talk about that later in later chapters. So for any assertion about an estimate, there will be an opposite statement. So if I claim that the population mean mu being 5.8, but it could also be true that mu not equal to 5.8. So this is like the opposite statement to my belief. So we want to decide which of these two is correct. So if you think it as like a criminal trial, the defendant is guilty or they are not guilty. So it's very similar to that. Our testing will be innocence until proven guilty. And we will use the sample data to decide that. So trying to understand this, being innocent until proven guilty is that we would consider the non-hypothesis, like our belief is true, unless we can like prove there is something with it, there is something wrong with it. So to be formally start saying how do we do the hypothesis testing, we will firstly get our non-hypothesis and alternative hypothesis. So the non-hypothesis, we will put it as H now. So from the previous example, the non-hypothesis is the one we initially believe we're assuming that is true. So mu equal to 5.8 inches. And the alternative hypothesis is a contradiction. So it can be like three different type of alternative hypothesis. Either is a two-sided, like mu not equal to 5.8, or mu greater or less than this 5.8. So this two is called a one-sided test, and this unequal from the alternative hypothesis is called a two-sided test. We will see, later we will talk about that. So we reject the null hypothesis if we find, so we reject this null hypothesis if we can find enough evidence that this null hypothesis is wrong, and we will see the alternative, and the same is similarly as saying the alternative hypothesis is true. We find evidence for the alternative hypothesis. So this is like innocent until proven guilty, and similar as now, it's now hypothesis until prove alternative hypothesis. So you often will see people will say we reject the null hypothesis, or we fail to reject the null hypothesis. So we are assuming this null hypothesis is true when we do this testing. And if we find some evidence for the alternative, we would reject the null. Or if we do not have enough evidence, we would say we fail to reject the null hypothesis. Well, this might be a bit mysterious. Why do not say you accept the null hypothesis? We will have a slide specifically answering that question. So we will start introducing the steps of this hypothesis testing by example. So this is from the textbook. A general belief that everyone gains 15 pounds for their first year of college. It's called freshman 15. And if we let this mu being the true average weight gain in the first year of college, and we want to test it out whether the freshman 15 is true. So this is, we want to test out whether this this statement is true. So this is how we get our null hypothesis. When you say we want to test something, so this would be your null hypothesis. So freshman 15, you gain 15 pounds. So this mu being 15. And the alternative hypothesis would be the opposite, which is mu not equal to this 15. And suppose we have a sample, a weight gain from n objects, and we could just look at the sample mean. If the sample mean, and we expect that this population mean mu should be like close to your sample mean, because if you take the expectation of your sample mean, it should be mu. So we expect that if mu differs from 15, so would this sample mean x bar. So mu is the population mean and x bar is the sample mean. But it's more powerful that we consider the standardized sample mean, assuming that the under the condition that we assuming that the null hypothesis is true. So just simply consider this x bar is not really enough to make a statistical testing. So we would consider this standardized sample mean. Well, in order to standardize it, we have to get the distribution for the sample mean. So if we assume the null hypothesis is true, we can find the sampling distribution of the sample mean being this. And we talked about this before. And we can, because we are assuming the null hypothesis is true, so we can just sub in the null hypothesis value, mu0 equal to 15 into this distribution. And we can put our sample standard deviation, we use this small s, so that we get this approximate distribution for this x bar. So now we get the distribution for x bar. Next, we can standardize it. So we standardize this x bar to a z value. So minus its mean and divided by its standard deviation. So this is the standardized sample mean. And we will actually call this a test statistic. And when this null hypothesis is true, this z value has approximately a standard normal distribution. So this is after you standardize this x bar, you get this standard normal distribution for this z. So yeah, I mentioned this z is a test statistic, and we can calculate this z if, so for example, we got a sample mean being x bar being 13.7, and we plug it in and also get our sample standard deviation and the sample size, and we can calculate a z value just by plugging this test statistic. We get a z value being negative 2.8. So this is how you get a test statistic. And generally speaking, a test statistic, it is a function of the sample data. So we plug in data from our sample, right? X bar, this small s and n, and we use it as a basis to decide whether or not we should reject the null hypothesis. And how do we make the decision? We will see that after we introduce the p-value. And well, in this case, well, I'm not going back. So this z value, it's a standard normal. The mean is 0. So standard normal, mean being 0. So for this z value near 0 would happen more likely when the null is true. You remember this this bell curve for normal distribution? So if it's near 0, it will be more likely. This Z value would be more likely to be located around 0 if this null hypothesis is true. So which means this mu is equal to mu0. So it will be more close to a standard normal. And if Z is far away, then it's more likely that null isn't true. Well, so we'll still use this curve to define a p-value. So we got our test statistics, right? So this p-value is the probability of finding this test statistic as a contradictory or more to the null hypothesis as the one you found. So it would be, or people would say, the p-value is a probability of observing observing the data being more extreme than this test statistic. So, well, in this plot, it shows you one-sided. This is for a one-sided test. How do you get the p-value, which is like it will be as extreme as this test statistic or more extreme than that. So which is to the right of your test statistic. So this plot should corresponding to alternative hypothesis. The alternative hypothesis being like mu greater than like mu0. Well, this is just to illustrate what is a p-value. So it's just a probability finding this test statistic being a contradictory or more contradictory to the null hypothesis. Because if you think like under this bell curve, if it happens on the tail, like very far end in the tail, like either it's one side, left, right, or both tails. If like the probability of observing that is small, like on like very end of the tails, so that means your null hypothesis may not be true. So it's calculated as we're assuming the null is true. So if the probability is tiny, like the tail area that you got is tiny, maybe it's random chance. Maybe the null is not true. Well, another concept comes with the hypothesis testing. It's called significance level alpha. And we actually mentioned this many times when we do the confidence interval. We do like 95% confidence interval, and 1 minus that 95, which gives us 0.05. That's actually our significance level alpha. And so like formally, we define this as, and we distinguish between where we are comfortable drawing the line, like drawing a line of rejecting the hypothesis or not. We use this number alpha, and we call it significance level. And we should determine this alpha before the test is done. And we said that if the p-value is smaller than alpha, we reject it now. And it's in favor of the alternative. We reject the now, that means we're in favor of the alternative. So what we are saying with this, if there is a smaller than alpha probability of this happening by chance, if H0 is true, so this alpha is tend to be small. Remember, we use 0.05. If we have like a smaller than 0.05 probability of the data that you are observing, under the condition that this H now is true, we reject that H now, because the probability of observing it is so small. So in that case, we would reject it. So we would often use alpha being 0.05 or 0.1, 0.01, and the most often used is this 0.05. And that's also like most often used confidence interval. We would always see 95% confidence interval. That's the most common one Okay. Well, we introduced quite a couple of like concepts when we do the hypothesis testing, and we would have two more, I guess, three more concepts before we really get into the steps of the testing. So it's possible to make errors in hypothesis testing, and the easiest example is that in a jury trial scenario, you can let a guilty person go free. That's definitely an error, right? And you decide they are innocent. And you can also find an innocent person to be guilty of the crime, convicting them. So this, like if you, like for the first bullet, you let a guilty person go free. Oops, yeah, you like, well, let's focus on this table first. So this is the decision you made before we really define which is which. So this is a decision you made, and this is the truth, like being innocent or being guilty. And so if a person who is actually guilty, but you let them go free, so you got a type 2 error. And for the type 1 error is that you get this defendant, you convict them, but they are actually innocent. You made a type 1 error. Remember, our null hypothesis in this scenario is always the person being innocent. Well, if this confuses you, I have this like formal definition of this type 1 and type 2 error. So for type 1 error is that you reject the null hypothesis. You reject the null hypothesis when it's actually true. So this is a reality, and this is your decision. And this type 1 error is also called a false positive. So positive, normally it means there is something wrong. A false positive, that means the decision you made is wrong. So you reject the null hypothesis in this case, but the null hypothesis is actually true. And we define the probability of making a type 1 error is alpha. Remember, alpha is the significance level we just defined. So there is a connection between like type 1 error with that significance level. And the type 2 error is that you did not reject the null hypothesis. We failed to reject the null hypothesis. And when in fact, it's false. In fact, the null hypothesis is false. So it's also called a false negative. And we define this probability of type 2 error is beta. Well, actually in engineering, a type 1 error is also called a false alarm. Let me see. So there are two. One is called false alarm, and the other is called misdetection. Yeah, the first one is a false alarm. So you made an alarm, but there's nothing wrong. The type 2 error is called misdetection. So there is something wrong, but you did not detect it. So this is the two types of error you can make when you do hypothesis testing. And there are some relationships between this alpha and beta we just defined here. Alpha is the probability of making a type 1 error, and beta is the probability making a type 2 error. So they are inversely related. One goes up, the other goes down. So yeah, this is just reiterating what is this alpha. And we can actually control the probability of a type 1 error by our choice of the significance level, right? We said we have to choose the significance level before we do the test. So the significance level is the one we chose. So we can control it. But for more serious consequence of a type 1 error, we should use a smaller alpha. So for example, suppose a convicted defendant would get death penalty. So in that case, we do not want to make a type 1 error. So we will use a smaller, yeah. Right, we would use a smaller alpha. So if a defendant is actually innocent, we would hope that the probability of conviction is definitely smaller than 0.05. We would use a much smaller one. Yeah, and also when I think for clinical trials, like when like FDA or like a pharmaceutical industry, when they develop new drugs, they do not want to make this alpha too big. So yeah, this is a slide I mentioned that why we would say we do not accept null hypothesis. We would always say we fail to reject the null hypothesis. So they are not the same. If you look at the example of this courtroom trial, remember the null hypothesis is always our defendant is innocent. The alternative is that it's guilty. So if the jury acquits the defendant, this does not mean that it accepts the defendant's claim of innocence. It does not mean it accepts the defendant's claim of innocence. It only means that guilty has not been established beyond a reasonable doubt. So we did not find enough evidence to prove that this person is guilty.
Make a decision. No? I mean, you have to choose if you stay with the no or if you go with the alternative, right?
Right. Yes. So for this one, I'm just saying, if like for example, we have already like did our trial or made our hypothesis testing, we rejected. We fail to reject if the conclusion that we have, we fail to reject. So people might ask, why don't you just say you accept this null hypothesis? So this is just like a analogy of saying why we do not say we accept the null hypothesis, is that we just did not get the evidence to show that this person or like the null hypothesis is wrong.
Do we accept the alternative hypothesis?
Yeah, I think you can probably say that you accepted the alternative, but you would never say you accept the null hypothesis. Yeah, you just cannot. You did not prove. You did not find evidence to reject that, but that does not mean you accept it.
For the significance level, how do we determine it? Because from statements in the slides, we have to focus on the first.
Right. Yeah, this is more of a subjective decision, but we always have like a guideline, a rule of thumb to follow, right? So normally people use 0.05. There's like no reason for that, just that's the most commonly used because well, that's probably people think 0.05 is a relatively small number. So we would think 0.05 being the probability making a type 1 error is okay. So it is a relatively small number. But if you think 0.05 is too big, then you can choose 0.01 or 0.001 if you want to be like conservative.
Most if we don't choose difference, we kind of however difference values. So who know the right person? So do you have positives, your answers to merge?
Well, this is something like you predetermined. Well, many people, they kind of cheat after they get the p-value because they want to get a significant test. So they change the significance level, so that they can make the claim that your hypothesis testing or the test is significant. Well, that's actually not the right thing to do. Or you have to decide, well, alpha being, let's say you decide to use a conservative significance level being 0.001. So they are all like relative. There's no specific rule.
So for the alternative, do you also determine the
Well, we will talk about that actually. We actually want to make alpha and beta both being small because that's a probability of making error. We do not want to make error. So we try to make both small, but they are negatively correlated. One goes up, the other goes down. It's like that. So this is the one that when we talk about the beta thing. Well, this beta, the probability of type 2 error, is related to the test power. We want to get a big power of test. So we want this beta being small as well. And this power is the probability of making a correct decision. So to reject the null hypothesis when the null hypothesis is false. So this is the definition of power. And this is the relationship with this beta. Power equals 1 minus beta. And in the book, there is some like theory, like work out how to compute the power for a z-test with known value of sigma. Sigma. But it's one of the few situations where there is simple formula available. So we can use the function power.t.test in R to compute the power of a test for you, and also give you like calculate the sample size necessary to get certain power. Well, I don't think we would have any question asking you on this, but it's more important to understand what is type 1 error, type 2 error, and how do you do the hypothesis testing step by step. Yeah, I guess that's the most important. So let's get to the, oops, let me see. Oh yeah, there's no, oops, yeah, there's no problem. The example comes later. I have just give you all the definitions will be used in hypothesis testing. And now we can do this hypothesis testing. So we will look at the case for testing the population mean. And we actually look at it in our example earlier. And this is called the z-test because we use the standardized normal curve and we calculate that z value, right? Yeah, just like we did for the confidence interval, we first consider there are several different scenarios we consider when we do confidence interval. Similarly, when we do this hypothesis testing, we have different scenario. Like the first case would be, we know the population of this distribution is normal and sigma is known. And also the case when n is large and the population distribution can like approximate it to normal. And the sigma are not known. And also when we have a small sample, how do we do a t-test for the mean of a normal population? So these are just corresponding scenarios, similarly as in confidence interval. So here we go. This is the steps for doing a hypothesis testing. So the first one, you will write out this null hypothesis, H now. So mu being this mu0. This mu0 would be in the question statement given to you, or this is the belief that you have about the population mean mu. And the test statistic for this z-test, it looks like this. Yeah, and the sigma, yeah, this first case is when sigma is known, so we have this sigma. And alternative hypothesis can be mu greater than this mu0, or like less than or not equal to. So you can have different types of alternative hypothesis. So I will give you a trick. How do you get this alternative hypothesis? Because this is always easy. The null hypothesis is always equal to some number where you can find in your question statement. Yeah, we will talk about that. And this p-value for each corresponding alternative hypothesis. So if we have this alternative hypothesis being mu greater than mu0, so the p-value would be the area under this bell curve to the right of your test statistic z. Remember the bell curve we just saw when we defined the p-value? It will be that case on the right tail, corresponding to this greater than sign. And if your alternative hypothesis is less than this mu0, and then when you calculate the p-value, it would be under the curve to the left of your test statistic z. And if it's not equal for the alternative, then the p-value when you calculate, it would be like the summation of this two tail area. Well, because it's symmetric, so we can do this 2 times the area under the curve to the right, either to the right or to the left. So you can do this 2 times this single tail area. You get the p-value for this double-sided alternative double-sided test. So this is in the case where we have a normal population distribution, and we know the population standard deviation sigma, so we can plug it in directly. Well, the steps to do a hypothesis testing. So the first one would always be identify the parameter of interest and describe it in the context of the problem situation. The parameter of interest, here we are focused on mu, right? And the second, determine the null value and state the null hypothesis. And also third step, give the alternative hypothesis. The null hypothesis is always easy. It's always like mu, if mu is the parameter you're interested in, mu equal to mu0. It's always equal to something. And the alternative hypothesis, depending on the statement, like depending on the theory you want to test, that would determine your alternative hypothesis. And once you have your null hypothesis and the alternative hypothesis, now you can write down your test statistic. like a z value that we calculated.
Do we always do the alternative hypothesis, or you have to determine it yourself?
You have to determine the alternative hypothesis, and that's a very important step.
What parameters are you supposed to use on whatever scenario that you're presented?
Well, there is actually a trick, like when you do when you determine the alternative hypothesis, where I will tell you exactly when we like look at example here. Yeah. So this is the steps. Like you identify the parameter of interest, write down your null hypothesis and alternative hypothesis, calculate your test statistic, and well, in order to calculate your test statistic, you would have to get like the sample size or like the small s sample standard deviation stuff and plug in and then determine your p-value. Once you get your p-value, you can make the decision. If p-value is smaller than alpha, you reject. If it's greater than alpha, you fail to reject the null. Well, this is the steps. Let's look at this example. Well, I feel like there should be an example. Well, I give an example of the of getting the alternative hypothesis and null hypothesis. Let's just look at this one. A manufacturer of sprinkler systems used for fire protection in office building claimed that the true average system activation temperature. They claim that the true average system activation temperature is 130. And we collect a sample of n equal to 9 system, tested, yield a sample average being 133.08. 131. Why I said 133? 131.8. If the distribution of this activation times is normal with standard deviation 1.5, so we know it's normal distribution, and we know the population standard deviation sigma is 1.5. We're asking, does the data contradict the manufacturer claim at this significance level? So we want to make a hypothesis testing at this significance level. And this is the theory, the belief that we have. The true average system activation temperature is this. So, well, when you see this, like we're talking about like the average something, we know it's talking about a mu, right? This is the parameter of interest. And for the null hypothesis, it's always equal and to the number that you can find from the claim. And the alternative hypothesis, so it can be like either it's unequal or greater than or less than. So when you see that the claim is like something is some number, that means you would put unequal. But if you see something like they claim the true average system activation temperature is greater than 130, then your alternative would be greater than or less than, that corresponding to alternative being less than the value that you can find from statement. But once you get your null hypothesis and alternative hypothesis written down, you can calculate the test statistic. Find the right formula. Like this statistic is like this. You just plug in whatever you have. This mu0 is this. So H now would always be mu equal to mu0. So this mu0 is 130. And we know the population standard deviation being 1.5 and divided by your sample size. Just plug those in and you get this Z value. Well, for this statement, we know that the alternative hypothesis is a mu not equal to 130. So looking at here, correspondingly, how do you calculate the p-value when the alternative is that mu not equal to mu 0? Is that 2 times the area under the curve to the right, or to the right of the test statistic of the absolute value. If you focus on the right hand side of the curve, it will be always positive, right? The value on the x-axis, which is the test statistic, will be always positive. So this thing in the parentheses is the one on your left tail, on your right tail, sorry. It's on the left tail, on the right tail, sorry. It's so to calculate the area on the right tail, it's always 1 minus the CDF. Yeah, so 1 minus the CDF. And don't forget it's 2 times that, because it's a 2-sided test. You have 2 tails because they are symmetric, so that you can do the 2 times just one of your tail area. So in this case, this p-value is greater than 0.01. Remember, we want to do a test at 0.01 level of significance. It's greater than,
So we reject the,
we fail to reject. We got a larger p-value than our significance level. Yeah, so in this case, that means the probability of seeing the probability of observing the data under this null hypothesis is 0.03, which is greater than like the cutoff probability or alpha. So we cannot reject. We fail to reject this null hypothesis. Yeah, if this p-value is less than your significance level, you reject the null hypothesis. So this is, the data does not give strong support to the claim that the true average differ from the design value of 130.
so we have p-value, the form of the 1 minus, is that the standard value?
You mean this phi here? Yeah, this is from the standard normal. So in R, you would do p norm,
Okay.
like p norm, and then you put the value you will get. I mean, for this thing,
We went 1 minus, or 2.
1 minus p norm this value. Yeah, it's very easy to get confused.
That's signal in parts 3 of the Q norm.
So this is not 1,000.
Yeah,
But to get the 2.16.
yeah. This. Oh, I remember it's a p norm.
Oh,
So it's 2.5 by 1 minus.
Yeah.
The syntax will be 2 multiplied by bracket 1 minus p norm.
Yeah, let's just test it out, because I remember it's p norm. Yeah. Okay.
So
Oh, probably if that's the case, what did I get? Oh, I did not get the. Right, PT gives the distribution function So I'm just using T distribution instead of normal distribution. This one gives you, oh, distribution function is the CDF. Q norm.
Also include the mean and the standard deviation for the premium to get the final answer.
Oh, because this is a standard normal. So you do not need to give it the mean and the standard deviation. So it by default, the mean is 0 and the standard deviation is 1. This is strange. Did I get?
And you're right, it was a few hours. I don't know. How long is it? Is it with no argument?
Oh, I didn't upload my R markdown. Well, this is strange. Why it does not let me?
Not the final answer. I think it's good.
Yeah, I think it was good.
I think it's 0.0308. That was the answer.
Yeah, I was.
Yeah. What I did was Q norm of 2.16. 1 minus Q norm of 2.16, and the final answer was probably.
Well, I'm having trouble with this R. Well, this is very much strange.
There's Q norm.
Yeah, so it is P norm.
Yes, Q norm. I got the right answer.
Yeah, sometimes I also got confused. Either it's P or it's Q, because Q is like corresponding to the quantile. It's always confuse you. But yeah, I recall it's a P norm. Well, anyway, it's good when you are not sure. It's good to check it out in R. Okay, so. Okay, so, well, this is the example for a z-test with known normal distribution and population standard deviation. And what if we do not know it's a normal distribution? When we have large sample size, we can use the central limit theorem. So we can still use the z-test for the populations that are not really normal, but we have a large sample size. And also we could do not know the value of sigma, and we do an estimation from our sample to get a sample standard deviation to plug it in. So this is saying when we're not sure about the distribution of the data, but if we have a big enough sample size, we can still use this z-test, and we plug in the sample standard deviation for the population standard deviation sigma. And it's just similar as before. And this test statistic Z would follow a standard normal under the null hypothesis. And how large is large? Again, we would need a sample size greater than 40. Okay, so, well, similar with the confidence interval that we talked about, when we cannot use this central limit theorem to assume normality, if our sample size is small, but we still want to do a hypothesis testing, we would use the same result like here, but this standardized thing now is called a T statistic because it follows a T distribution with n-1 degree of freedom. So this is just correspondingly to the confidence interval that we learned. How do we calculate it when we have a small sample size? And we would have to do, in the hypothesis testing, we would have to do a t-test. And the rest will be the same, just change your like p-norm or whatever to pt. So because now it's a t distribution, right? And you need to supply the degree of freedom n-1. So you will still use your sample size here and also use your sample size here. So, well, we have an example here. Let me see. Yeah, this is the case when we have greater than something. Let's just talk through the example for a t-test. So a study is conducted to check the effectiveness of a therapeutic treatment to teenage girls suffering from anorexia. The variable of interest was each girl's weight change. Weight at the end of study minus the weight at the beginning of the study. And the weight change was positive if the girl gained weight and negative if she lost weight. And it's desired to check whether the treatment had some positive effect. Whether the treatment have some positive effect. Focus on this sentence. This is what we want to check. This is what we want to test at. And have positive effect. That means the mean weight change would be greater than 0, right? Remember, you put this on your alternative hypothesis because your null would always be equal. So your null hypothesis would always be equal to 0 for this case. And for this alternative, because we want to check whether this treatment has positive effect. So the alternative is mu greater than 0. And collect some data. Sample size being 29. And the weight change for this 29 girls has sample mean 3 pounds. And standard deviation S 7.32. So 29, it's not greater than 40. So we would use a t-test. So as I said, you have to identify null hypothesis and alternative hypothesis. Alternative hypothesis is the key. And the test statistic, plug in whatever you find from the statement, you get the test statistical value, the t-value. And the next, get your p-value. And if you like traditionally, people would just look at a t-table. You will find this is the only information you can get if you just look up a t-table. But now we can use R. We can find like the exactly p-value here. So this is 0.018. And we wanted to do a test at the significance level of 0.05. So comparing your p-value with this alpha, so p is less than your alpha, 0.05. So at this 5% level of significance, we reject null hypothesis because this probability is too small comparing to our significance level. So that we have enough evidence to claim that the treatment has positive effect. So we reject the null hypothesis. Well, in the previous example that we failed to reject the null, that we would always say that we do not have enough evidence to reject like whatever statement in the null hypothesis. Okay, this interpretation is also important. Like after you make the decision, you have to like make the statement in the context of the scenario, of the question statement. And there is some side notes here about comparing the hypothesis testing and confidence interval. So, so the conclusion, well, we talk about this example first. In this anorexia study, a 95% confidence interval for this population mean weight change is 0.2 to 5.8. And we infer that because they are like all this interval is above 0, it's greater than 0, right? So we infer that the population mean weight change mu is positive because all the numbers in the interval are greater than 0. So, or we could see in the other word, the 95% confidence interval does not contain the null value 0. So, well, I have this formal statement here. Like the conclusions about mean using a two-sided significance test are consistent with the conclusion using confidence interval. So when we use this confidence interval, we would look at if the null hypothesis value, your null value, like mu0, to see if it's within your interval or not. That if it's in the interval, you would fail to reject or not. If like this p-value is less than like the corresponding significance level, this is when you reject. When the p-value is greater than your significance level, you fail to reject. And your 95% confidence interval would contain the value in your null hypothesis. So these two things are would always be consistent. They would always agree. Okay, and we would have to talk about how are we going to do test for proportion p. Well, before that, we can do a z-test for any parameter. Like p is just a different parameter, right? Different than from the population mean mu. And we can use the population proportion to model how we can generalize the large sample z-test for any parameter. So I think I should put this one after this. Well, anyway, if we define this theta hat to be an unbiased estimator for theta. So if you think this is your x bar or your p hat, this is your p hat, would be an unbiased estimator for p, right? We assume that the standard deviation of this theta hat, when the null hypothesis is true, is this sigma is known. And our null hypothesis would always be like this, theta equal to theta 0 for some desired value. And the test statistic, you just plug in this theta hat minus this theta 0 divided by its standard deviation. So it's all like very similar format. So this is just generalized to any parameter. And we compute the test with the same procedure as before. So it can generalize to any parameter. So example would be this theta equal to is just the population proportion. So remember, well, this theta being P and theta hat being P hat. And when the null hypothesis is true, so that is P equal to P0, right? And you have to calculate this sigma. And if you remember the standard deviation for the P hat, we have a formula for it. So you just plug in the true value for P, which is P0, plug it in. So P0 times 1 minus P0 divided by N. Taking the square root, you get the standard deviation of the P hat. We use this P0 because we are assuming this null hypothesis is true. So when we do the test, we are always assuming the null hypothesis is true. That's why you can plug in the mu0. That's your null value, right? So now we get our P0 and we got this sigma. So plug everything in, you get this Z statistic. And once we get this, we know how we are going to the next, how we are going to do the next. Get the p-value and comparing to the significance level, make our decision. So that's all the slides. Yeah, like if you're comparing this one to this one, it's the same thing. It's just plug in the value you calculated. Yeah, it's everything are the same format. But like the details, it's a bit different. Like the standard deviation, how do you calculate it for the population proportion, and previous.
Just use the first one and use the second one because there's so many parameters we need to start calculating and stuff.
Yeah. Actually, if you remember one, like remember the formula for like for either for the T test, remember this one. It's always the one like you put your sample statistic like X bar or P hat minus their mean and divided by their standard deviation. This is the step of called standardization. Once you standardize them, you can get back to like Z or T distribution. Once you get the distribution, you can like look at the curve and calculate the probability stuff. So that's like the basic we get back. But we have some example here. Well, I have the R code. I think R code is also included here. I didn't give you the. Okay, this is better. Go away. Okay, so well, I have this example for the hypothesis testing. I'm thinking I'm not going through like step by step because it's really self-explanatory. So, and the code is also here. Like, how do you do the test? Like the statement. So, well, the case thing I want to emphasize is that like once you get your alternative hypothesis, so this is maybe one of the key points. Get your alternative hypothesis is, well, let's just read the statement because we haven't talked about like this scenario yet. So boys of a certain age are known to have a mean weight of mu equal to 85 pounds. A complaint is made that the boys living in the children's home are underfed. As one bit of evidence, we have this n equal to 25 boys of the same age, and we find a mean sample mean being this this much pounds, and it's known standard deviation, population standard deviation, and based on this information, what should be concluded concerning the complaint? Concerning the complaint is here. A complaint is made that the boys living in this children's home are underfed. Underfed means their weights should be less than this, right? So this would corresponding to your alternative hypothesis. Yeah, so this is how you get this case step. Yeah. And by the information provided to you, you decide if it's a z-test or it's a t-test. And plug things in, calculate your p-value, make the decision. Well, the p-value, like when you calculate the p-value, like you know you are going to calculate the probability of z less than this like z value that you z statistic test statistic you calculated. So when you are not sure about this, you always go back to this page. This is really tedious stuff. Like just by practice, you can know this better. Like how do you do the p-value corresponding to different alternative hypotheses? Like you should use the right tail or left tail or both tails. So in that the first example we have mu less than 85, so it would corresponding to the left of your z statistic. To the left, that would be, oops, this is this one. Directly this p norm. So remember this p norm is corresponding to the CDF. CDF is something less than something. It's the left tail probability. So this is how you get your p-value. And this is the example going through the z-test. Yeah, yes.
Just before you start with that one. So what you get at the end is you confirm that that place, the kids are like are underweight, right?
Yeah, so
you confirm that the area they're underfed.
So that's the thing we want to test it out. And for the conclusion that we have after we get the p-value, we have to compare it with your alpha level, right? This alpha level, this p-value is less than alpha.
Yeah.
So we reject the null. So the null hypothesis is mu equal to that, so that you will see the we feel or we did not find evidence p less than 0.05. We rejected the null hypothesis. That means we would
So you can say yeah, those
yes, they are underfed. Yeah.
So what mu is being subtracted from one? Like, you know,
Oh, so yeah, I know what you are asking. So if this alternative is mu greater than something, or like p greater than something, you do the 1 minus the CDF. Yeah, when you do the 1 minus, that corresponding to the right tail area. So if it's less than, remember the CDF is just something less than something, so you can directly use the CDF. Yeah, right. When we, like for this case, we reject the null hypothesis. That means we would see the alternative is true in favor of the alternative hypothesis. I'm kind of tired of like repeating repeating this again and again. But this is like how you learn things. Well, I highly encourage, because this would be very similar as like your homework or the exam questions. If you are not so sure about how do you do the step by step, you just go through this three. I think I have three or yeah, three example. For example, I have this one for the propulsion. Well, I just gave you the formula from the slides, and this is how you are going to implement like step by step. How do you calculate the p-value? So I'm not going to like reiterate on this anymore. And just remember this confidence interval and the hypothesis testing would be key parts for the second part of this class. Well, I guess we can just stop here. Any questions? And you will have the homework corresponding to the hypothesis testing. We have that. So we can use that. Have that. Oh yes. Oh, this is the file. Yeah, it's already on Blackboard, as well as the slides. Yeah. Oh, also, no problem. So I'm going to set up a kind of a survey, because we already got our midterm. I think it's time to get some feedback from you guys, like how I could improve like the way I talk, or like the way we go through lectures. I think it's important to get feedback so that I can make changes accordingly. So just pay attention. You might see an anonymous survey coming up on Blackboard. Okay, yeah, I'm trying. I'm trying. Yeah.
All this syntax and the examples that you've given us actually are very helpful to me.
Okay, it's great to hear that.
So
Yeah.
I need some more time to do categorizing all these things. That's good. So
Okay, then that's good. Yeah. All right, I think we can stop here. Now stop the recording here. Are you sure you want?
The homework is